Okay, so we're on the chapter on eutrophication or nutrient pollution, and it deserves its own chapter because it's one of the big issues in lakes and has continued to be one of the big issues in lakes. We already talked about toxic cyanobacterial blooms, how every summer they're getting worse because of global warming. But this was an issue that kind of came to the forefront in the 60s. And there was a big controversy over whether phosphorus or carbon was limiting primary production in lakes. And the phosphorus, the detergent companies make the most efficient and cheap way to make detergent is to use phosphates. They argued that, well, downstream from sewage treatment plants, the algae are limited by the amount of carbon in the water for photosynthesis, by CO2 in the water for photosynthesis. And as the sewage is respired away, the CO2 is higher, and so that's what's stimulating primary production. David Schindler in the experimental lakes area in Canada took this lake and put a plastic curtain right here. And this side received carbon and nitrogen, and this one received carbon, nitrogen, and phosphorus. This one had big cyanobacterial blooms. This one stayed clear. This one picture probably had more to do with getting the idea of phosphorus as a limiting nutrient across. And picture's worth 1,000 words, as they say. So that gets us to chapter 18. And we're going to talk about what do I mean by trophic state, nutrient pollution in lakes, why it matters, natural and cultural processes of eutrophication, the relationships between the nutrients, water clarity, and phytoplankton, and then how we mitigate eutrophication in all these different things, habitats, and some specific case studies. So historically, people based the definition of trophic state solely on the algae in lakes. And I call this autotrophic state now. But as we've got into understanding it better, we realize that there's a lot of aquatic habitats that are more based on materials produced outside of the system. So autochthonous, self-feeding, autotrophic is photosynthetic organisms in the lake or stream or wetland. Allochthonous is material coming in from outside, and so some systems have a heterotrophic state. So this is, you can think of, for example, a shaded, a forested stream where much of the energy is coming in the form of dead leaves, right? Well, it can be quite productive even if the nutrients are fairly low, and it has a high heterotrophic state and maybe a low autotrophic state. But we'll talk about this, when I talk about this heterotrophic state or autotrophic state, I will focus in on the algae a lot in the lakes because that's where a lot of the attention has gone. But if you think about sewage treatment, dumping biochemical oxygen demand in and causing the oxygen to disappear out of the system, that's because they're polluting the heterotrophic state of a stream, not the autotrophic state. And this is really useful to classify trophic states because it tells you what the natural range of trophic states of systems might be. So for example, we could compare our cleanest lake here in Kansas to the cleanest lake in Colorado, and the cleanest lake in Colorado would be considerably less productive, just because the natural processes lead to higher production here. So what we need is a global system. And there's two of those systems are here. The first one on the left is from the OECD, Organization of Economic Cooperation and Development. And they got limnologists from all over the world around to say, what are their lakes? How do they classify them? And then they got ranges of chlorophyll that are related to that. And the categories are, we've already talked about oligotrophic, mesotrophic, and eutrophic. And ultra oligotrophic is even more so, like Lake Tahoe or Waldo Lake, which we've spoken about. Hypertrophic are things like sewage treatment ponds or some of the really heavily algal bloomed systems. We can see that these are probability distributions, that if you have chlorophyll at 10, you might be in a system that's really low, lowly hypertrophic, you're more likely to be in a eutrophic or a mesotrophic system. But because of the variability over years and such that you know, these are not like solid bins or categories. In contrast, Bob Carlson came up with a system that links together the things that lead to high chlorophyll to make a trophic state index, going from 0 to 100, which basically maps to logarithmic distributions of Secchi depth, phosphorus, and chlorophyll. So when we have a very deep Secchi depth, we tend to have low chlorophyll, less than a microgram per liter, and low phosphorus, and that would give us a nice score down in here in the 20s. If we have a lot of phosphorus, like in an algal bloom, might be 200-300, the Secchi depth is going to be maybe 20 centimeters, and the phosphorus would be quite high. We would have a high trophic state. So there's just sort of two ways to look at this. From the manager's point of view, you say, okay, I don't want to have a eutrophic lake, I want a mesotrophic lake. So how far do I have to push this system to get down into this distribution? How far do I have to push the phosphorus down to get to the Secchi depth that I want, or to keep the chlorophyll below a certain level? So why does nutrient pollution and resulting in algal blooms matter in lakes? Taste and odor problems are big ones. Many municipalities use surface water as their source for domestic drinking water. And when you have algal blooms in those surface waters, in those lakes and reservoirs, they can really cause problems. And I don't know, do we have anybody in the class that's from Wichita at all? And Wichita has these problems. Okay. So you guys know that in the summertime, maybe still the drinking water from the tap gets that sort of musty flavor to it. It's a geosmin. It's the same kind of sort of a dirt. It's flavored. Some people don't like beets because it has a slight amount of that flavor. And you can get the smell when you turn on the shower with the hot water, especially. It's there's that musty smell that pops out. Max is not on Wichita water, so even though he's in Wichita, Lawrence is having some troubles with this, and it can also come. It has to come from river eutrophication. That sometimes there'll be large masses of algae on the bottoms of rivers, on the benthic of rivers. In addition, algae can be toxic. We talked about algal toxins, and these toxins can move through water treatment systems and cause problems for the people and for the organisms that live in it. People are less willing to pay to live on or near or recreate on eutrophic lakes. This can cause economic damage to areas. And then fish kills. We've already talked about if you have big algal blooms, then the chance for oxygen disappearing when the light's low or during the winter time goes way up, and you can have fish kills associated with it. So there's a lot of different reasons why this might be a problem. And then I referred earlier to natural and cultural eutrophication. Natural eutrophication is there's this classical view that lakes slowly become more eutrophic and eventually they become shallow and turn into a marsh and then a meadow. And a lot of this is built on sort of the upper Midwest, Southern Canada view, the Northern European view, where many of those lakes that they're studying, the small lakes they're studying, were left over from glaciers. They might be kettle lakes or something like that. They're not very deep. And it's true, they fill up and eventually they turn into a marsh and then a meadow. But there are some lakes that this is not necessarily true. So for example, Lake Baikal has been in existence for millions of years. And it's cycled, but it's been oligotrophic for much of its history because they can do the paleolimnology and go back and see there's oligotrophic species in there. When the glaciers went away, it became more eutrophic, and that's because there's a bunch of disturbed glacial till and nutrients that washed in, but then it kind of went back. So there's not an inevitable cultural eutrophication, natural eutrophication that goes through successional processes. Cultural eutrophication far exceeds that, and cultural is from humans. So us putting nutrients into lakes and streams and wetlands and groundwaters for that matter. So to understand and manage eutrophication, how much nutrient should we allow in? Do we produce as many fish as we want to, or do we get a system that has fish kills, requires to understand these relationships between nutrients and water quality? So here's an example from lakes from Val Smith, who passed away a few years ago. He was a professor at the University of Kansas. And on the x-axis is the total phosphorus in the epilimnion of the lake. And usually it's an average over the summertime. And chlorophyll in the epilimnion of the lake, usually it's an average over the summertime. And we see that while there's variance in the relationship, there's a strong statistical relationship between phosphorus and chlorophyll. And you could use this to say, okay, if I take my phosphorus from 100, where I've got about maybe 20 to 30 micrograms chlorophyll per liter, down to 10, I might be able to get it to 3 or 4 micrograms per liter. The other thing that this says is that the nitrogen to phosphorus ratio is important. So when we have not much nitrogen, you can draw a line between these with the least nitrogen, lowest nitrogen to phosphorus ratios, intermediate nitrogen to phosphorus ratios, high nitrogen to phosphorus ratios. So nitrogen is relatively more limiting here, little intermediate and least limiting here, meaning for each unit of phosphorus, you get a higher yield if there's a lot of nitrogen around than if there's not so much nitrogen per unit phosphorus. Okay, again, we're back to ecological stoichiometry. So another question of the day, if there's a manager that says, I want to take my lake from 100 to 10 micrograms per liter phosphorus, and it's going to cost you $1 million to retrofit your sewage plant to accomplish this. Why is it important for the public when she or they say this? Why is it important for them to understand the inherent variance in this graph? So what I'm saying is, like, if you look at this number, right, this could be 3, right? But it could be 10, it could be 1. Yeah, the variance is important because you could have a system. Yeah, you don't want them to think they're going to get an oligotrophic lake. You don't want to make promises you can't keep. So they do need to understand there's natural variability, and this could be from year to year, or maybe a tropical lake has more subtropical lake in Florida has more chlorophyll per unit phosphorus than one that's in Minnesota or something like that. So yeah, you have to be realistic about the variance, and this is an order of magnitude variance inside of each of this envelope, right? So that's important for people to understand that, sort of best case and worst case scenarios. But we still can use these to say, okay, if we've got X amount of phosphorus, on average, we can go from like this 100 here, boom, down to this amount of chlorophyll, which is about 100 micrograms per liter, which would give us, a meter of Secchi depth. And then we could say, from the public's point of view, you don't want to say, do you want 100 micrograms of chlorophyll? They're not going to know what you mean. They want to know, well, how deep can you see the bottom? What is the Secchi depth, basically? They'll say, well, I want a lake that's clear enough that I can see 3 meters down, right? So then you'd say, okay, well, that's going to require us to get down to about, maybe 1 microgram per liter of chlorophyll or something like that. So this is and there is an error in here. This is micrograms per liter. So I should fix that. Okay. I keep forgetting to do my laser pointer. This should be micrograms, not milligrams. Okay, so to mitigate the eutrophication, there's a couple of things that you have to do. You have to control nutrient sources, which Emma already said. Yeah, I can, and Emma says, do I get extra credit for finding a mistake? Well, it's my mistake, so I just get to be sheepish about it. But that's the way it goes. Nobody's perfect, right? Okay, so we got to think about control of external and versus internal nutrient sources. And maybe people will treat in a lake. And then one more aspect that people think is important is backfoot removal. The fact is what people want is they want a lake that is like a crystal clear swimming pool that has really big fish that you can catch easily in it. And it's an unrealistic expectation. They don't want any macrophytes, even though that's where the macrophytes, where the fish can reproduce and their young can survive predation. But and we see this again and again in my field. So what are these steps to mitigating external loading? And this is a complex diagram, but this is what managers go through. And some of you, if you get into this, these agencies or consulting, this is sort of where you're going to end up going through. So the first, you have to identify if there's a problem. You know, if nobody cares, then maybe it doesn't matter. Second, you have to characterize the system, looking at things like lake morphology and measuring the nutrient inputs and describing the watershed. You know, is there a feedlot upstream? Do septic systems dump into it? Is there a sewage treatment plant upstream? Is it a shallow lake or is it a really deep lake? Does it have a large watershed to surface area? What's the shoreline development index, which we talked about, all these kinds of things. Then you have to identify what might be feasible ways to control the nutrients. So maybe you want to put buffers in around the cropland, riparian buffers, decrease the amount of fertilizer additions, time them so they're not happening when there's rain. Put in terracing in the cropland to make sure people are tilling their crops across the slope, so runoff doesn't just bring a bunch of sediment with all its phosphorus in. Improve your sewage treatment plant. Ban phosphorus and detergents. Those might be some things that the regulation would be required, or voluntary buyouts or something or other. Then you can project the relationships between in-lake nutrient concentrations and management effects using those this type of graph. So this actually is a graph that talks about the loading and equation, and we won't cover it in detail, but basically what it's saying is that you got to think about how fast the water's turning over in the lake and how much nutrients flowing in. So if you have just a little lake and a river's flowing through it, right, you're not going to be able to, it's not going to last very long, but whatever you do upstream is going to change things really quickly. If you have a huge lake and it's been phosphorus has been dumping in for years and it's continuing to cycle inside, it's going to take a long time to get that loading under control. Then, as we talked about, you use these relationships with chlorophyll, and it's there, and phosphorus, and it's correct there, micrograms per liter, and Secchi depth, and say, okay, are the costs of these controls justified based on in-lake improvements? And then the final thing is that if you do put the control measures in, you have to continue monitoring it to see if the lake has improved to meet expectations. And this is where giving the public realistic expectations at this point is important, because then you can go back and say, okay, did it match? And if it didn't match, why didn't it? So where's this phosphorus and nitrogen coming from? And we can think of a bunch of different places that it could be coming from. So these are the ranges of nutrient loading that we can see in natural systems. And we can see that cropland is putting a lot of phosphorus in, kilograms per hectare per year, and a lot of nitrogen. Idle land and forest is pretty low. Pasture is somewhat low, maybe a little bit higher. But if you fertilize pastures with manure, it's pretty rich in nitrogen, so you can basically get a lot of nitrogen runoff. Feedlots dump a ton of nutrient in. It's really difficult to control the runoff from feedlots because the cattle are excreting so much. And what to do with all that manure, like fertilizer, that one's tough. Residential is high, maybe not as high as some cropland, but people tend to dump a lot of fertilizer on their lawns, thinking, oh, if I dump twice as much, it's fine, and they're not very cost limited. Different commercial activities can have a wide range of those, and industrial activities. Forest is low, can be high if it's nitrogen saturated from atmospheric deposition. And we see that this wet and dry deposition are really important from the atmosphere here. And that agriculture and urban industrial really creates a lot of dry and wet deposition from emissions from burning things and such. Okay, so when you're planning that, when you go back to this control strategies, you have to think about what's upstream and what's coming into the atmosphere. So one of the questions that oftentimes comes up is you say, well, this lake is dirty, we should clean it up. And the people that are, it's going to cost to clean up, and say, well, how do you know it wasn't naturally clean, and what is the cleanest it can be? So one of the things that we've come up with was an idea that, part of the problem to figure out the natural nutrient concentration is that you have large areas that just don't have any native habitat left. So this is a plot from Kansas, from a variety of watersheds in Kansas, that has the percent watershed in cropland. And you can see that, there's a couple here that you might call reference, right? But even those have 10% of their watershed in cropland, and some that are up around 80%. Well, there's a real relationship here. First, it says, well, if you don't want nitrogen running in, you don't want to have a lot of cropland, right? Or you need to mitigate that nitrogen somehow that's in the cropland. But the other thing you can do is say, well, what happens if we have none of the watershed and cropland, like we did historically before people started dumping fertilizer on crops? Well, we can just take this line and statistically go back to where it crosses this axis here. And there's also statistical techniques to say, okay, what's the uncertainty as we go back, so you can get an idea of the range. And use that to get at what the natural concentrations are. So you may remember back when we were talking about nutrients in the last chapter, I put up a graph that had natural nutrients, nitrogen, and by all the ecoregions, and current. And that had a lot of more phosphorus, a lot more nitrogen in most of the watersheds. How do we get that natural amount? This is what we had. This is important for managers, because this allows them to say that there's a difference. Oh, I'm excited about this. Okay, it's time to stop.